In this video, we're going to look at a concept loosely related to limits called continuity. Continuity is a big concept for calculus. There are certain conditions that need to be met for continuity in order to determine some upper level things like derivatives, but that's kind of beyond what we're going to be doing in this class. So the idea of continuity is visually, can we draw the graph without picking up our pencil? And if the answer is yes, then we're going to say that the graph is continuous. We need a little bit more formal idea, formal concept, because when we get to the piecewise functions in a little bit, visually figuring out continuity isn't going to help us. So the first thing we want to do is figure out, is the function defined at the value? In other words, if they're asking us to evaluate the continuity at, like, let's say x equals 2, we want to first of all know, does that function actually exist at 2? If it doesn't, then it can't be continuous. The second thing we're looking for is, does the limit exist at that value? Does the value from the left and the right approach the same thing? And the third thing we're looking for is the limit equal to the value of the function? If you remember back to our last video, we talked about limits being intent, what the function wants to do. The third question is basically saying, hey, it wants to do this, does it actually do it? It wants to go to 4, does it go to 4? And if the answer is yes, then we have a continuous function. If any one of these three things are false, if any one of these three questions we answer no to, then we can't have a continuous function. And there's different reasons for each, which we'll get to. So on our graph, we have 4 different values that we want to determine, is the function continuous or not. And we're going to start off at the point -3. When I go to -3, first of all, I'm going to look, is the function defined at that value? And I definitely see when x is -3, there's definitely a solid point. That line goes straight through that point -3, 3. So I'm going to say yes, the function is defined at -3. The next thing we're looking for is, does the limit exist at the value? If we go from the left and the right, are they approaching the same thing? Well, from the left, looks like it's approaching 3. From the right, it's approaching 3. So I'd say, yeah, that's definitely true. The limit does exist at that value. And then, are they equal? Is the limit of the function equal to the value of the function? And so what we're looking for here is, the value of the function is 3 and the limit is also 3. And that is definitely true. And so what that means is the function is continuous. If we continue that to the next one, look at x equals 0. Is the function defined at that value? Well, if I look at this leftmost piece, it doesn't look like it because we've got that open circle. But on the rightmost piece, we do have a circle that's been filled in. So it is going to be defined at that value. But where we have a problem is the limit. As I approach from the left, I'm approaching 0. When I approach from the right, I'm approaching -2. I don't approach the same thing from the left or the right, so the limit doesn't exist. And at that point, I can stop, because if the limit doesn't exist, the third question is pointless, because the limit can't equal the function if it doesn't have a limit. So it is not continuous, and there's a very specific reason for that. If you look at the graph, as we approach from the left, we're approaching this value and immediately jump down. What we call that is jump discontinuity. So it's changing functions really, really fast. At x equals 1, there is definitely a value here at 1. And if I approach from the left or the right, I get that exact value, which would be -1. So that's considered a continuous function. At x equals 3, I have a problem immediately. Because of that open circle, the first question, is the function defined at the value, is a no. So that means the function is not going to be continuous. It's going to be discontinuous. And the reason for that is point discontinuity, or the type of discontinuity. There's a hole in the graph. Big problem. Now, when we're looking at piecewise functions, our tests are still the same. We want to first figure out, is it defined at the value? If it isn't, then we know there's going to be a hole in the graph. We've got point discontinuity. Then we want to look at limits. As I go from the left and the right, are the limits, are the values the same? And if they are, then we're good. Then I want to double check and make sure that the value and the limit are exactly the same. Now, in a couple of these, there's really not a lot to test, because when I go and plug in 0, 0 fits in this interval between -2 and 1. So if I'm going to evaluate that, my strategy is to take that number and plug it in. Well, by plugging that number in, because 0 is definitely defined on this interval, I know I'm going to have an output. And that output is whatever I plug into here. And so if we're in the middle of a linear piece without any breaks or holes or anything like that, we know that part's going to be continuous. So at 0, because it fits directly in this interval, that's going to be a continuous piece. And same thing with 2. 2 fits directly in between 1 and 3. No reason to believe that we're going to have any holes or anything in a linear piece, so that's continuous. So now we're looking at all those other regions where we've got potential breaks and changing over from one function to the other. So at -2, let's say. At -2, first thing I'm looking for, is the function defined at -2? So it doesn't look like it's so far because there's no equal sign here, so I don't have a value at -2, but I do here. So the first question is it defined? Yes. So I'm going to continue. The next question I'm looking for is, does the limit exist? As I approach from the left, plugging in -2, that gives me 1. If I approach from the right, that also gives me 1. The limit exists. And the value of the function is when I plug -2 into here, and they are equal, so the answer is yes, it is continuous. At x equals 1, again, first thing I'm looking for, is the function defined at 1? Nope, it's not. We have a 1 here and a 1 here, but no equal sign, so I never know where to actually plug that in to get the value at 1. So again, if it's not defined at that point, then that means there's going to be a hole in the graph, so we call it point discontinuity. And then at x equals 3, it is defined at 3, and that last piece. The next thing I'm looking for is the limit. If I plug in 3 into this leftmost piece, I'm going to get 11. Plug in 3 to the rightmost piece, I get 7. The limit doesn't exist. So if the limit doesn't exist, but the function does, then I have jump discontinuity. So again, it really boils down to our 3 questions. First things first, is the function defined at that value? If it is, keep going. Second question, is the limit defined at that value? Does it have a limit? If it does, keep on going. The next thing, usually if the first 2 are correct, the third one's going to be correct. Does the limit and the value of the function, they have the same value? And if they do, then we have a continuous function. If we don't have a defined value at the function, it's point discontinuity. If we have a value but not a limit, it's jump discontinuity.